Well, thank you, Mr. President, for your kind introduction. So, for next few minutes, I'll be talking about our study of shear delamination in thin brittle high ductile interface. So, I will be talking about our motivation and objective, the experimental procedure that we have followed, and the numerical simulation that was used for the validation, results, and the discussion on the assumptions that was made for this study, and finally the conclusion. The work was driven by the important application of two materials, aluminum and low density polyethylene, known as LDPE, in packaging industries. A normal fruit juice or milk packet got some additional layers of material like paperboard or decor layer, each of them serving a specific purpose for the conservation of content inside. But however, here I'll be talking about aluminum, LDPE, and the laminate of these two materials. Interestingly, like any other composites, the adhesion between two layers or the strength of the layer, you can also say the delamination energy release rate largely dictates how the mechanical property of this laminate will be finally. So it's important to know the delamination energy release rate for the composites, and this work tries to find an alternative way to measure this. So at present, end-notch flagella, or sometimes maybe latrine, is used for measuring the shear delamination energy release rate in the composites. But we are studying very thin and flexible aluminum and LDPE films, which are most of the time less than 10 microns. So these procedures are not quite helpful. Zero-degree pitch testing is another way for finding this shear delamination energy. But our study was based on the interesting observation that during a pre-centered cracked LDPE and aluminum laminate tensile test, along the propagation path of the crack, significant delamination occurs. So with a simple animation, I can show you this path. So this is the crack propagation path. After this part you can think of. So this delamination occurs. And this is a tensile test down this laminate, and we can see this delamination area here. It's quite significant, and if you used colored fluid, that's what we use as normal colored fluid, to penetrate the delamination area, and so that it can be measured easily. So we used that technique together with the plot digitizer to measure the delamination area here. Another interesting observation was when the delamination area was studied under electron microscope, it showed that the delamination surfaces are quite smooth, which is a signature of shear fracture. And together with this observation and finite element simulation, we come to the conclusion that it can be said the delamination happening in this area is dominantly from shear. So in short, what we try to do or claim is when you have these two materials, aluminum and LDPE as a single layer, and you have a pre-centered crack, and try to get a force displacement tensile test, and hence the energy required to fracture them, and compare with that of a laminate of these two materials. So there will be an energy difference for fracture. And we try to relate this energy difference to the shear delaminated area, and find the shear energy release rate for this thin, flexible laminate. So that's the objective, overall objective that we had here. So that's a simple force displacement curve for the test down in this laminate. So the black one, the black curve shows for the laminate, the force force displacement curve for the laminate, and the green one for LDP, and the red one for aluminium. Now, interestingly, when I say that we want to separate the energy curve for driving the cracks, the curves doesn't look quite similar. Like as in laminates, it has a higher peak and a lower displacement, but as a single layer, LDP is quite compliant. But still we have done that, and for these assumptions I have some remarks that I will share towards the end of this presentation. So our idea is to then add the energy for fracture of aluminium and LDP together and subtract it from the laminate, and to claim that this area, difference in this area or area under the curve or the energy was due to this delamination. And interestingly, it was found that the delamination that was occurring here, they are quite similar to each other. So a assumption could be, a good estimation could be measuring just one delamination area of one street here and just multiply by 4, so to get the delamination areas all over these places, and the energy you have as a difference of that got from the test surface testing. So for verification by finite element modeling, we have to do some additional testing, like single layer continuum aluminum and LDP, and also the peak testing, the material modeling that was used. We used elastic with von Mises plasticity and softening tool. So we had some peak testing. So this was to facilitate the normal delamination energy release rate for this laminate. But for shear, of course, we'll be using the measurement that we get from the method that was proposed in this study. We used bilinear fraction separation cohesive law, and that's the measurement that we finally found for shear energy release rate. Interestingly, it's quite high, almost 9 times when it's compared to the normal energy release rate of delamination measured by 90-degree peak test. So after the simulation, finite element simulation that was done in Abacus, it was found that the delamination was occurring along the peak of this propagation path, and we could capture to some satisfactory extent the response of experimental and the simulation response. They were quite good agreeing with each other. So we could also go to the tip of this laminated response of this composite. And so this simulation was done to check if the boundary condition that this experiment is offering is does it facilitate shear delamination that as we could gauge from the electron microscopic studies that we have done earlier. So a delaminated cohesive element along the crack tip was measured for the energy release rate, and it was found it was highly dominated by, for the given boundary condition, as shear, to be shear. And yeah, so that was actually all that we tried, a simple idea to have the energy difference and measuring the area of delamination and relating that this is due to shear, and come to the conclusion that we could get a good estimation of shear energy release rate for delamination. Of course, this is applicable when one of the layers or one of the substrates are very compliant compared to the other ones. So, like in here, the aluminium layer or aluminium foil could fracture in very early, and that the LDP together with when it's laminated is supporting or providing good enough boundary conditions that can facilitate like a 0-degree peel, and hence the shear delamination. But there was quite a big leap when I said that we could make the difference between the energy of fracture between the laminate and the individual layers. But then we have this higher peak in laminate, as I said earlier, and the single layer LDP is quite going through a larger strain. So there, at least I can say that after the fracture of a laminate or during the fracture, during the fracture of an LDP layer, it goes higher displacement, that's for sure. But most of the energy was stored as elastic energy away from the crack tip and has been used for driving the force or driving the crack, the later part of this of the experiment. And whereas in the case of a laminate, in difference with a single layer LDP, the laminate in laminate after the aluminum foil has been broken or fractured, so it facilitates a very small length LDP tensile specimen. So this together with the strength of aluminum gives a higher peak. It can be assumed as the peak here with the aluminum together with the peak of LDP, so we give a higher peak. So of course this is not very much conclusive. We have also tried to do a effect of length on LDP or a pre-cracked specimen length, how the length affects, because in case of the laminate, the length is quite small here compared to a single layer LDP, and it seems it's reasonable if we see the result or effect of length of single layer LDP, and also if we study the fracture surface or the amount of plastic deformation that happens in a LDP or in a single layer, in laminate and in single layer LDP. So now after that, I have already talked about the conclusion that I try to come on, that this energy difference can be used as a base for finding the shear energy release rate of delamination. And the nature of this delamination is we can have support that this was shear. The nature was shear from the finite element simulation and also the electron microscopic study. And as I said, that although there should be some additional source of energy difference, it could be from the manufacturing process of laminate in comparison with single layer substrates. It could be pressure, it could be temperature. That makes the difference between the energy, fracture energy between the laminate and single layers. But we could get a good estimate of interfacial shear energy release rate using this method. So just to be useful. Thank you.